gotten to watch quite a few of these today, and this kind of knowledge sharing is truly what makes our industry stronger. So I appreciate everybody's attendance here as well. As Alex said, I'm BJ Silgenberg. I've been with Bar Engineering for 10 years and worked for the Corps of Engineers, St. Paul District for a couple years before that. Today I'm going to talk about the Island Lake Dam sluice gate replacement project. And I was searching for bigger themes, things outside of the geeky technical structural engineering stuff, which I'll happily talk about. And it really came down to a couple things that I could glean from this project that I'm seeing as themes in other projects as well. And that's that we're increasingly having to do more with less. A lot of the infrastructure in the dam world is 100 years plus or minus old. This project was built in 1915, and we're not doing full out replacements of these dam structures. We're having to repair them. And if you keep watching the ASCE report cards and the squabbling over public funding in Congress and et cetera, we're not exactly seeing bounds of money to be able to replace these things. So we're having to think creatively about how to do more with less. And the few tools we do have more of in today's world try to employ to the greatest extent on this project, one of which is analysis. We have computing power far exceeding what they had even 5 years ago, 10 years ago, and certainly back when these dam projects were built in the 1810s, 1920s. And the second is our ability to collaborate quickly, to include multiple voices, opinions, etc. That during the design process is stronger today just with our communication. So I'll try to talk about how we leverage these as much as possible on this project, as well as geek out on all kinds of structural engineering. Quick agenda. I'll go through the background of just where Island Lake Dam is, what its purpose is, and then I'll set out the problem, define the problem, some preliminary design we did to try to help our client, Minnesota Power, focus in on where we should head for the solution, and then dive into the detailed design, which kind of has three main pieces. There's some piers, an arch, and some phasing way to think about. So I'll dive into each of those. Briefly touch on construction. Construction was actually kind of complicated because it was hard to see. So there wasn't a lot visually to show from that phase. And then entertain any questions or answers out there. Well, hopefully I would have the answers. Couple acknowledgements. So the owner is Minnesota Power, they're a division of Elite, and they're located or headquartered out of Duluth, Minnesota. And JF Brennan Company was the contractor on this project. And I acknowledge them not only as partners, but they were collaborators in this. I mean, we all hit this problem as a collective problem and all talked freely amongst ourselves for collective solutions because the owner has to operate this after us as the design engineer are long gone. And the contractor perhaps has the biggest price tag out of this, so they have a huge influence on what things cost. So having everybody on the table when you're making design decisions is key, and those two organizations operate as collaborators. Let's dive into some background on Island Lake Dam. We'll go up to, you'll see Duluth, Minnesota at the southwest end of Lake Superior down there. So Island Lake Dam is on the top, that's the top arrow, and it dams up the Cloquet River. Cloquet River goes to the left down to that second arrow where it hits a confluence with the St. Louis River, and then the St. Louis River ultimately drains into Lake Superior. The importance of Island Lake Dam is kind of interesting. It's really a big battery. As the flow goes down in the Cloquet River or the St. Louis River, it gets dammed up in the Thompson Dam down kind of near Duluth and Superior, Wisconsin. And there's the Thompson Hydro Plant, which is a 72 megawatt plant. That's the biggest one, and I think the oldest one, or near the oldest one in Minnesota. Notice I didn't say there's a hydro plant at Island Lake Dam because there isn't one, but its importance is pivotal because it has an operating band of about 10 feet through its FERC license. So it will store up water in the spring and the summer, and after the summer boating season and et cetera is over, the late fall and the winter, it will use up that 10-foot operating band. And you can see from the aerial there that it's got a big footprint. It's a big reservoir. So it'll drop that 10 feet out throughout the winter to optimize the Thompson plant downstream. In addition, there's the natural environmental consequences and recreational consequences that the reservoir holds as well that add to the criticality of this project, which was built in 1915. We'll zoom in a little bit more. Here's the two outlet structures. In the upper portion, there's a relatively new labyrinth auxiliary spillway that I don't think has been since it was built in 2017. I don't even know if it's been used, but a couple times. And then our project is going to focus on the primary outlet structure, which is composed of two pieces. On the right side, you'll see, and I use the original terminology from the original drawings, a log sluice and a wasteway. I'll define those a little better. So the wasteway, the gates, and that's what we're going to be focusing on for this project. The gates are down at the bottom of the reservoir. In fact, probably the lowest point in the reservoir, near the lowest point, is those gates. And it's about 50 feet down, and 5 sluice gates. Then on the left side of the right picture there, you'll see the log sluice way, which, as the name might indicate, back when they were logging this area and this dam was in, that's how they would let the logs pass through. And there's a big structure under there, a steel structure called a bear trap that had this big articulating feature that would lower that whole section about 25 feet. It's not been used in decades, probably over a half century now. So it's locked in place now. But the primary purpose of the log sluice way, that they primarily control the waterway that way. And it's the wasteway for floodwaters. And then the winter water level actually goes below the sill elevation of the log sluice way. So they have to drain through the wasteway in the wintertime as well. We'll zoom in a little bit more. You obviously can't see the gates of the wasteway, which is on the left side in this picture. They're 50 feet down underwater. That building there is the actuator house for those gates. And then on the right side is the sluice gates that are higher up. And there's 5 of those as well. That entire structure is about 60 feet wide. So there's about 30 feet in each side. And again, our project will be focusing on the left piece. So we'll clean that up here with just a simple model to look at the components of that are important. Highlighted in a magenta color are those sluice gates down at the very bottom. There's some dewatering piers that go about halfway up. I'll be showing this image again in a couple slides and add some more context. That's critical to the complexity of this project. And then another important piece that I'll touch on as well is an 18-inch thick concrete arch, which is an interesting feature. I haven't seen anything like this in another dam in this area or of this era. There were some arch dams used in the Southwest, super efficient, but we had to have some sensitivity to how we loaded this arch, because arches are incredibly efficient for a nice uniform load, but as soon as you start to upset that, we had questions about how well that relatively thin element that's 100 years old was going to weather this construction project. So let's lay out the problem and talk about how we did our initial design. The gates are 100 years old. I'd have lots of problems at 100 years old as well. They were seeing them, lots of excessive leakage. One of the gates was a good several inches high at its most closed setting. It was to the point where even getting a rover to inspect was difficult because of the flows, and divers, it certainly wasn't safe for divers to get down near the gates. You're actually seeing an original picture from January 5th of 1915 there on the right, and they're craning the original sluice gate down to install it. And that in lies the big problem. The gates were leaking bad enough that they couldn't get divers in to swap it out. There have been several sluice gate projects that I've been aware of, a couple I've been a part of that have been diver led. This one could not be one of them because it was leaking so bad. And there was no good way to bulkhead off the water on the downstream end easily. So the complexity of the project was largely, how do we dewater this at 50 feet down to get these gates swapped out? Here's that image again, and you'll notice that the first dimension there at 26.5 feet above the sill, that's where the piers die off. I said this reservoir was used as a big battery for the Thompson Hydroelectric project originally. I suspect they used to dewater this reservoir by quite a bit more, and they at least designed the project so that they could dewater down to that elevation 1345 or lower so that they could go maintain those gates. But for decades now, they haven't been able to do that. I walked onto this project when it had already started in our office to start taking on the engineering, and I came in with this great idea. Why don't they just lower the reservoir that low? Um, to which I essentially got laughed off. There was basically no legal recourse or environmental recourse that they could do that, even though it would drastically reduce the cost of the project and significantly simplify everything, because those piers were designed for that. What they weren't designed for is about 50 feet of head, which is what we had to throw at it to dewater this and get these swapped out. So then becomes the complication of how do we dewater down there. There were 4 primary options that were given to Minnesota Power that we developed. Number 1 is to extend all of those piers up and basically operate it as it was originally intended, but to a higher elevation. Um, the issue that got tabled when that was articulated is that somehow we need to reinforce the original piers because they were designed to 25 feet or so of head, not 50. The second one is to just extend the outer elements and create a large cofferdam across the whole thing, dewater at one time. The third option was a hybrid of those two. And then the fourth one was dewatering or bulkheading from downstream, at which point the leakage would no longer be a requirement or an issue, because you'd be controlling that flow such that now divers could get down. So the dewatering would ideally be simplified for number 4, but the construction would be intensified. Anybody that's familiar with dive work, that cost of, say, tightening a bolt underwater versus above water can be 5 to 10 times as much. Ultimately, the client and us too favored option 1, where we extend the piers up. But then in lies the complexity of trying to get the lower piers to be suitable. One thing that was attractive to the owner about this option is the ability to just dewater one at a time and maintain just one gate. They lose a significant amount, more than half of their flow capacity, if they take out all 5 of these gates at one time. So the desire to be able to take out just 1 or 2 at a time was pretty heavy, and they liked that aspect. So that kicks us off into the more detailed design. The preliminary design did a quick look at the pier elements, what a pier that was 2 feet thick, designed for 26 feet of waterhead, would do under 50 feet of waterhead, and found that it was indeed over capacity, but it was a simplified one-way design method. So one thing we pulled out pretty early was the use of finite element methods on this, because it is reinforced in 2 directions. There are stiffening elements that are struts that go from pier to pier, which you see through the triangles and you see the spikes in the stress profile where those elements are. And then on the right side in these images is where the arch would connect. So this is pier 1. There was symmetry on the arch, so there were 2 types of inner piers and then abutments on each side. And I won't bore you with the details of each one individually. We'll just look at a kind of a standard approach of how we attacked this. The solid red line that goes across is the delineation between the existing and the new. And the new, the world is our oyster. We can essentially design that with modern concrete, modern steel for whatever we want. That wasn't a big problem. It's everything down below. And the issue with these piers is their reinforcement for a 2-foot thick pier was a 1/2-inch bar, square bar, at 12 inches on center. So it was actually unreinforced. It was less than the ACI 318 minimum of 0.0018 times the area gross. So it wasn't even establishing the minimum required area of steel for structural concrete per ACI 318. When I crunched the numbers on plain concrete, ignoring the rebar and even putting in all the design factors that ACI requires, I found that the plain concrete strength exceeded the reinforced concrete strength. That said, we did not use that strength just because we weren't sure of the condition and the cracking state. So when you look at the stress profile, we had multiple areas that were of concern that we needed to reinforce. And we were able to put struts from pier to pier in a number of locations, but we could not do that in the lower 8 feet because that's where velocity, actually the lower 10 feet, because that's where velocities were heavy enough that we couldn't have a strut impede the flow there. Not only would it reduce their flow abilities, they also pulled out a Polaris snowmobile out of the bottom of the reservoir when they were dewatering this during construction. So there's debris down there that could have risked clocking one of those struts. So ultimately what we decided to do at this point in the design, and I say this point because this design project was by no means linear. It took lots of different twists and turns, mostly to reduce the project cost. But we were still chasing after the owner's original goal of being able to dewater each of these bays separately and independently. So we pulling out every tool we could think of to try to make that happen. And the two main tools we could think of and employed was to strut across from pier to pier, basically create this steel grid to reinforce those piers because they had virtually no capacity in the original pier sections. Now down in the flow area, down by the gates, there we had to employ a steel plate option where we essentially create a composite section out of the pier itself. Now you'll note that on the middle 3 bays there, we've got piers sitting there, or I'm sorry, struts sitting there in the flow path. And that's because we have a chicken and egg problem there. We can't put these steel plates on before we're able to dewater, and we can't dewater until we've got the steel plates on. So what the construction phasing would require if we proceed with this option is to dewater the entire thing at the risk of losing over half the flow capacity of the project and get some temporary struts in place. At which point then you can pull out the outer bays, bulkheads, and allow flow through those bays during flood events. And then you can work on putting these steel plates, which was an incredibly tedious process. We sketched out for that with something like this, where it's a 3/8" steel plate with holes at 12 inches on center. The contractor, through conversations with them while we were developing this, said they'd likely put the plate in place and then core hole the drills so they knew exactly that the holes were lined up with the plate, pull the plate back. We also need complete continuity between these anchors, the concrete and the steel plate. There can't be any slop or fudge in there at all. So you essentially have to weld it up together and then epoxy grout the anchors in and grout the annulus between the steel plate and the face of the pier at the back end of that. At this point, we took a pause in the design. The contractor crunched the number on how long and how costly it would be to do the steel plate retrofit, and it was quite an impact on the project costs. So the team got back together to talk this through with the client saying, we can't afford that. Let's go back to the drawing board. And at that point, it became a scheduling question because we essentially were back at a point where we needed to dewater all 5 bays at once. So they've reduced their flow outlet capacity and they need to take on that risk. And the way to manage that is to perform this construction during the winter time where they know their flows are significantly lower. The next piece we had to consider with this option, especially if we're going to dewater isolated piers on their own, is that arch. So we've got this 18-inch thick concrete arch. It's been holding up fine for 100 years, but we're going to now change by quite a bit how it's loaded. To illustrate that, we looked at 3 primary load conditions that were of concern. Actually, the first one on the left is not a concern. That's how the arch is loaded today. And as I said before, arches are incredibly efficient if they're loaded uniformly. As soon as we start upsetting that with point loads, and particularly with asymmetric loads, now we're starting to introduce, through asymmetry, but by virtue of that, we're going to have eccentricity and thus moment in the section in an 18-inch thick section that wasn't designed for it originally. So we were concerned with 2 on the right-hand side, particularly case 3 on the right-hand side. The second image down there on the second row there you're seeing is the loading that we employed. The third one is the deflected shape we got. And I'll say this is from a 2D frame model where we looked at a 1 foot high representative slice down at the bottom. But we wanted to get a little more refined than that because this actually was showing that we still had issues. So similar to our approach on the piers, where during preliminary design we did a 2D approach and then we employed a 3D approach through 3D shell elements. We did the same here as well. So we modeled up the entire arch. We have a much rougher mesh here. For the piers, we used a 6-inch mesh size, and here we used a 24-inch mesh size because the model was already starting to get kind of arduous, and it was still capturing the general behavior we were looking at. We did some sensitivity analysis on this and found the 24-inch shells got us close enough. And this would capture a couple things. Number one, it's hydrostatic loading. So obviously a foot up is a foot less hydrostatic load, etc. So it's getting lighter load as you go up higher, and yet the shape isn't changing. The second is you'll see some stiffening elements down at the bottom. Those piers that are in between the gates project downstream of the arch. So they're available essentially to help stiffen the section. They essentially brace those gates down at the bottom. And then there's a slab element down there as well that would help brace the arch. Those were not accounted for in our 2D analysis. We looked at it that way. So when we compared the 3D shell finite element models with the 2D frame finite element model, mind you, we found that load condition 3 was indeed the conservative one, or the most concerning one, and we found that it did fail by about 50% in its utilization. But when we do that with the 3D shells, we found that that goes way lower because its ability to distribute to those stiffening elements and vertically in the structure was so influential on that. The other thing I'll highlight through these numbers is just the change of the axial and the moment capacity in an arch. For those of you that may not be structural engineers, or your structural engineering coursework in college was a repressed memory, PU is your factored axial load or stress in the section, and the phi PN is your nominal capacity. Each of those have factors that are applied to them. For this design, we used Corps of Engineers approach, so it's pretty conservative. The load factoring was about 2.21. And then the moment, MU is the moment, that's your flexure in the section. And for this 18-inch thick, unreinforced, well, it's not unreinforced, but it's lightly reinforced, there's not a lot of capacity. So you'll see real fast we use up that moment capacity. Interaction is combining the two. It's taking advantage of the fact that your compressive stress from your axial load in the arch actually overrules or reduces or eliminates the tensile stress that comes from the moment. And the interaction equation, it's not a stress addition per se, it's the ACI interaction equation, which has a little more complexity to it, but that's what we employed here for the interaction. So that's the beauty of an arch, but it still has some sensitivity to it if you start introducing too much moment. But in this case, we were able to convince ourselves that we could essentially unload or change the dewatering condition in any one of these bays and still feel okay that the arch could handle it. The final piece that I wanted to talk about during the design phase is the phasing. When we looked at doing this project to be able to dewater independent bays at a time, the complexity of it didn't only bear out through the design of those steel plates and getting all those anchors in the right spot, with all the tolerances and et cetera that we needed there, but it also played out in the phasing. So we actually had a few phasing sheets that detailed out in total about 4 years of work over 27 steps to get this all done in a stepwise fashion. Because as you see in the bottom image there, there were certain points at which we could have certain gates open. And the other flexibility this employed is that they could do this work at virtually any time of the year, save springtime when you historically have your worst floods. So the complexity of this project also bared out in schedule, and we had to work closely with the contractor to understand what we're doing when and how they can handle that at any given time. So after we talked with the client about the cost of the reinforcement plates, getting those on the faces of the piers, and the complexity of the phasing, the duration of the construction, that's when, as a team, and mostly the client, decided, let's figure out a way to do this by dewatering all at once. And that's ultimately what we opted to do. So the risk there is that there was a slightly higher risk of needing to pull things out during the construction project. And that's mitigated through, number one, having the construction happen during the late fall and winter time, which increased construction costs a little, but it's doable. Actually being 50 feet underwater amongst all this mass concrete and adjacent to the reservoir, your temperatures of those elements that deep are a little closer to more consistent, 40, 50 degrees, even during your coldest winter days, which are formidable in Duluth. So that was doable. And then the emergency action plan, EAP, for dealing with a flood event would include that they would have to pull out the top bulkheads and essentially flood the site if they need to pass enough water. Keep in mind, we do have that labyrinth spillway, that auxiliary spillway. So all the dewatering elements on this project went 2 feet above the invert elevation of that auxiliary spillway. So if the emergency flood came at a fluke time of the year, winter or fall, late fall, there was a plan for how to address that. And that's how ultimately they decided to dewater all 5. The other thing they lost is the ability to dewater any one of these sections at once. And that's something they could go back and do in the future. And that was the discussion had with them, is that any of the elements, the steel plates or that lattice work of steel struts, still existed. Those could still be implemented by dewatering the entire system at once and putting those elements in if they decided it's worthwhile down the road. They did purchase enough bulkheads to dewater all of these bays at once because they had to for this construction project. So they kept those bulkheads on site and are able to do that. So that brought the phasing down to a much simpler process. Basically, in year 1, they took out a bunch of the supports on the upper left side there. There's some lateral supports to the rods that go down and control the gates. So they take those out. They extended the piers up vertically. That's all underwater work. Used a method called pre-placed aggregate for the piers, which turned out to work out pretty well. They lower the steel bar cage in, they lower the aggregate in, and then they pump in the grout mixture. The contractor felt that they could control the quality much better underwater with that process. And the results did indeed play out pretty well. They got a nice, smooth, intact mix out of it. Then they put in the struts in the new pier sections. Those were still required for the new design. There's some other walkway stuff on the upper right. And then in year 2, they came back and dewatered the entire site with the bulkheads and swapped out the gates. We'll look at construction real quick. One of the things that I want to touch at, and one of the reasons I don't have great photos of this construction project, was access, light, everything. So the face-to-face distance between those piers is 4 feet. When the bulkheads were slid in those piers, you're seeing the upper pier extensions there. The last one is formed up and the rebar's in there. The other ones have already been cast. When the bulkheads are in, you only have 2 feet between the face of the actuator building and the downstream end of the bulkhead. So craning things in on the upstream side was doable, but there wasn't a lot of room. Not to mention you have all those critical steel struts that you need to work around if you're going to lower stuff in the site there. That leaves the downstream end. There is that slab that's down at the bottom of that archway. You can see the arch, the condition of the arch as well, was another thing making us think twice about just changing the loading as we saw fit on that arch without thinking deeper about it. It's pretty weathered. and some sign of leakage in some places. Those openings that you're looking at, again, are the face-to-face width of a little higher there. Those piers are 1.5 feet now, so it gives you a little more breathing room by about 3 feet. So everything that they pulled down in there, they dropped in through those openings. And they've got the 5 openings there for each of the 5 bays. So all the old concrete and steel had to come out through that, and all the new elements had to go in. One of the ways they did that, you can see on the left side, is the old sluice gates, cast iron gates. And actually you can see the nose of that Ski-Doo snowmobile is over there as well in the left picture on the right side. And then this is rather unusual, but I believe it was Rodney Hunt was able to work with them on the gates to chop them up into 3 leaves. So they set each of those leaves down independently. The frame elements were all long enough and narrow enough that they could crane those in and then reassemble all of those gates down in the hole. This image right here, what I'm highlighting is a couple things. Number one, we knew we had to remove a portion of the pier to get the gates in. And because of the construction phasing, we were asked by the contractor during the design phase, can they blow out the pier on both sides, thus creating an opening? Keep in mind we have dewatering bulkheads going all the way down, and at the bottom they're subject to 50 feet of hydrostatic head that is pressing in to those piers. That turns the pier itself, the original pier, not only into a supporting element for the bulkheads, but it's now a flexural element between the base slab and then the portion of the pier where it reconnects and then sends the load into the arch on the right side of the left image there. So we had to analyze that section for that kind of flexural load. And in this case, we did use the plain concrete formulas, and because the steel reinforcement was just not helpful enough. And we were able to get safety factors, even employing all the conservativeness of the Corps of Engineer approach and the ACI load factors. We were still getting utilizations of 20 to 30%, which made us comfortable to let the contractor do this. The overall section was deep enough. It was something like 5 or 6 feet deep. So it's a 5 or 6 feet by 2 foot wide beam, essentially. And then the other piece that I want to highlight on this, we weren't 100% sure the quality of the concrete. Minnesota Power had done some coring. You can actually see one of the cores there on the right side during construction, but they did some coring in advance of construction of the concrete. One advantage of concrete is that it continues hardening all its life. So they were able to prove that they got somewhere in the 4,000s range. Even though it's old, kind of poor quality concrete, it's still in the 4,000 range just because it's been hardening for 400 years, or 100 years. That said, you don't know the mix, the vibration, all the other aspects that inform the quality. So what that means is we used a 3,000 PSI mix assumption on all of the existing elements. And then we used all those conservative load factors. But the final piece we didn't know is all that quality. So we wanted to do some monitoring. And what you're looking at right over there on the left is a distance monitor between the outer pier, which has water on the other side of it, and then the next one in. And we watched that displacement during the dewatering operations to see if it moved at all. And we had one on the abutment side as well. So one of the edge piers has water on the other side, the other one's earthen into the embankment. And we watched both of those piers super closely live while we were dewatering. And then those monitors stayed in place as well and had alarm triggers, though we weren't super concerned if everything played out fine within the first couple hours. There wasn't a lot that could come up after that would change unless water levels on the outside changed. So that monitoring was hooked up to alert critical members, including myself, via text if there was an issue. And then we had somebody local that could run out to the site if there was an issue. There was an alarm once from we suspect a temperature issue that happened on one of the sides. We had redundancy in this monitoring. So that's one other risk tool that you can pull rather than just say, we won't do this because we don't know. the concrete condition, or etc. You get what data you can, and then you can do some of this monitoring on site to give yourself additional comfort that things will be all right. And then one final observation we had during construction here that's kind of separate from these other talks is low strength concrete. This has happened on one or two of my other projects as well, but otherwise it doesn't happen at all. And that's where you get low strengths early on. Your 7-day breaks are lower than you expect. And then you get to the 28-day break, the one you're really hoping to get your design strength, which was 4,500 specified in this case, and don't get it. And then you start stressing out because do you have to be the consulting engineer that has to talk to the owner and the contractor about pulling stuff out or additional steps to improve the durability because your concrete's coming in low. But this was a good, the owner, in this case, Minnesota Power, always has a tendency, they were controlling the testing in this and just consulting with us, and they always pulled extra cylinders. And it's a good lesson to always pull quite a bit more, 2, 3, 4 cylinders more than you expect you might actually need. Those are so cheap to pull during construction. But as I mentioned before, concrete it's stiffening and aging its entire life. So theoretically, at some point, you will always get your design strength. And what I wanted to illustrate here is that it took over 120 days to get our design strength, or close enough to it that we're able to sign off and say, yeah, durability and strength, we're fine with that. Then I'm going to bring it back to those last two takeaways that I kind of kicked things off. With all the things that we have to do with limited resources, limited budgets, etc., design world, we're always being pressed to do things faster. The two pieces we do have at our discretion is we can do a better job analyzing and do more detailed analyses. The tools are constantly getting better. The computational power to do most of these models is a non-issue. Our phones could almost do them for us. And the second is that collaboration piece. It's always tricky because what the owner gives up is the ability to get the best price through bidding. But contractors and owners that are dedicated to pulling on a specific contractor and designer up front are committed to it because they think the cost savings in the end through that collaborative approach wins out every time on the bidding. And that's certainly, if you were to ask the team on this project, if you were to ask them their opinions, that's what they would share. So those are the two broader takeaways I got from this really complicated project that was mulled over by the same complexities that hit almost every other infrastructure project that I've been a part of. And that's, they always want it done cheaper, they always want it done faster, and it's really old and needs a lot of work. And you've got to make it fit within that. So with that, I'll leave it there. Alex, I think I'll send it back to you and open it to questions.
Great, thank you so much, BJ. Does anybody have any questions for him? You can type it in the chat or unmute yourselves if you'd like to ask directly. Okay, I'm not hearing any questions. If you do, you can go ahead and type in the chat. We can get that to BJ to see if he can afterwards. So, but if everyone could just thank BJ for his time here. I'm glad that you're able to see some of the other presentations today, and hope you'd hang around for the rest of the day. But thank you for your time.
Thanks everybody for attending. Thanks, Alex.